Alright, today we are going to be talking about solving cube root equations. Alright, we've kind of done this, a little bit of this here, but today we kind of have a big formal day for it here. So I guess we'll start out here with this question here. Got a warehouse, worker stacks identical cubed shaped boxes inside a 512 cubic foot storage container. There are 2 feet of empty space to the right of, in front of, and above the boxes. What are the dimensions of each individual box, and then how many of those boxes could fit in the space? Okay, so the way I would start this problem out here is it looks like we have at least a row of 4 boxes there on the bottom right here. So I'm going to call this length here. You can call it whatever you want. We'll say the length right here is going to be 4, and I guess I'll put x for the distance of each box, the length of each box, I guess I should say. So there are 4 of those, and then we know we have 2 extra feet of space. So we'll put 4x plus 2 right there, and that'll be this dimension. And then since all dimensions of this cubed box should be the same, we're going to assume all of those are 4x plus 2. And then remember, to find the volume of something, y'all learned in middle school, length times width times height. Okay, so we're going to take 4x plus 2 and we're going to multiply it together 3 times. So that'll be all of that stuff cubed. And apparently when I cube all of that right there, that's going to give me my total volume, which was 512 right there. Now, if you go and try to FOIL this thing out 3 times, the 4x plus 2, that's going to be kind of a pain, just because there's so many, there will be a lot of x's and stuff, and you have to do a lot of distributive property. So our way around this here is we're going to undo this cubed right here. So to undo a cube, we do what we call a cube root. We cube root both sides of our equations. Okay, so when we do that there, I think the cube root of 512 is 8. All right, and then the cube root of all of this other stuff here, those are going to cancel each other out, and then you're going to just be left with 4x plus 2. And then from there we can subtract over 2. And then we can divide by 4, which would get us about 3/2, which in the word problem I'd probably just call that 1.5. So that means each dimension of the box is 1.5 by 1.5 by 1.5. Okay. Now, as far as like how many extra boxes could you fill here, I guess if you only got a gap of 2 feet right there, you're not going to be able to put in 2 boxes there. So you're only going to get to be able to put 1. And then, they kind of give us a front and a top view here. So if you think about this, if we're going from the front here, this would be, I guess, 1, 2, 3, 4. I guess on this first one here it'd be 5, but it'd be 4 units back right there for both of those there. So I kind of like this top view. I just like to think, okay, if it's I guess gonna be 5 tall, each one of these here, if each one is 5 tall, you can just go and take all of these here and then multiply 5 a bunch of times right here. So you'd go 5 right there times, I think that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 times 9 right there, which would get us 45 extra boxes right there. And that's how you do that right there. Okay. All right. Now, sometimes they're not going to give you context. Sometimes they're just going to say solve this equation. And it's actually very similar to how we solved square root equations the other day. So we can do this here by just subtracting 5. We want to get that radical thing by itself. So that'd get us 6. And then we're going to cube both sides. So I'm going to cube 6, and then I'm going to cube the left-hand side. That'll cancel out. So that's 2x. 6 raised to 3, or 6 cubed, is 216. And then divide both sides by 2, and that would get us, I guess, 108. And that is it on that one there. Big thing here you want to make sure to do is isolate your radical, kind of like what we did the other day. And then, let's see what's going on here with this one. So we'll cube both sides there, and that would get us 5x minus 1. And then 4 cubed would be 64. And then we can add 1 to both sides, that'll be 65. And then 65 divided by 5 should give us 13. So pretty easy, nothing crazy going on. C is probably as hard as it gets right here. I'm going to take a sip of water here. All right, with this one, we'll subtract 9 from both sides. Okay, and then you got 4 and then times the cube root of x minus 12, I guess. And then once we subtract 9, I guess we get negative 16 right there. And then I guess we can divide both sides by 4. And that'd get us negative 4. Now, some people are going to say, oh, is this like the square root problem where if we have a negative on the right side, we can't do that? And then since we're, I guess, dealing with just a square root and then not, technically, we're not dealing with like, we're dealing with a cube root here and not a square root, we can actually cube root something and we can get a negative number when we cube root something. So this one's good to go here. So don't worry about that weird rule. That's only with, I guess, square roots. So we'll cube both sides here. That's going to get us x minus 12. And then negative 4 cubed would be negative 64. And then I guess we'll go and then add 12 to both sides there. And that should get us negative 52. So there's really not any, I guess, crazy cases in this case for solving. Now, we're also going to get some problems here that have these things here raised to fractions. And when you have something raised to a fraction, it's actually like you're doing a root of some sort. So this is a little bit of a recap. You should have learned this in Algebra 1. It's honestly not superly heavily covered in Algebra 1, probably like 1 day's worth of stuff here. But we had whenever you take something and raise it to a fraction here, like 1 over n. N is the power of the square root that you're dealing with here. So like, for example, if I had a raised to 1/4 right there, we would call that the 4th root of a. All right, and then sometimes you can have like true fractions where a and m are both some type of number. So like you could say a raised to like 2/3 or something like that. And then that would be the cube root. The cube root is always the denominator. And then you can write it 2 ways. You can write it as a raised to 2, or you can write it as the cube root of a and then squared. So really, like this one here is saying do the cube root first and then square it. But these are both essentially the same thing. It doesn't matter on the order that you do those things. So like I guess I have some examples here. You got x raised to 3/2, so that's x cubed, and then it's an implied square root right there. And if it's a square root, we typically don't write it. Or like with this one here, you have 8 raised to 1/3, so that's the 3rd root of 8 right there, which we can simplify. So notice we're working with the roots other than square roots. So this first section here is just converting them here. So we'll say a raised to 2/3 is going to be 8. That's the cube root. That's the denominator. So it's the cube root of 8, but then we're going to square it right there. And then another way you can write this is the cube root of 8 squared. So actually squaring 8 first and then cubing it there. And then I guess they want us to simplify here. So honestly, the best order to do this here, you could go, oh, and I messed that up. That should have been cube root there. But you could go and do 8 squared first and then cube root it. But to me, it's easier to go and do the cube root of 8, which is 2. And then we can say 2 squared, which is 4. And that would be your answer there. Notice here on this next one here, you have 16. So this will be 16. The power of the root will be 4th, so it'll be a 4th root of 16 and then cubed. So to me, we can do the cube or the 4th root of 16 easier. It's what times what times what times what gets us 16. So that'd be 2, and then 2 cubed would equal us to 8. All right, let's see here. We got the 32 raised to 4/5. So this will be 32. This will be the 5th root of 32 raised to 4. All right, and then the 5th root of 32 is 2. 2 raised to the 4th is 16. And then that is your answer right there. So yeah, they can simplify. All right, now these are a little bit different here. We're going to solve equations with these fractions here. And to solve an equation with a rational exponent first, isolate the power, then raise each side of the equation to the reciprocal rational exponent. The reason being, if we had, for example, I don't know, a raised to x over y, to cancel out a fraction right there, to cancel out a power, we can multiply by that reciprocal, y over x, and that's going to cancel out your fraction. Now, whatever you do to one side, you got to do it to the other. So now before you begin this problem here, you want to isolate x first. So we'll divide both sides by 7. We get 8. So that's x raised to 3/5, that fraction right there. Let me move this down a little bit. So we're going to raise both sides to the reciprocal fraction. So we're going to raise both sides to 5/3 right there. And that should cancel everything out on the left-hand side. So 8 raised to 5/3. A couple of ways you can do this. You can actually literally type that out into your calculator the exact way it looks. 8 raised to the fraction 5/3 and then solve it. But also we can convert it. Like say we didn't have a calculator in this case. We could go and do the cube root of 8 first and then raise that to the 5th power. Okay, the cube root of 8 would be 2. And then 2 to the 5th power, I believe that's 32. And that would be your answer. Or you can use your calculator. Just make sure you raise it to the actual fraction. So that's all you do. So raise everything to the reciprocal. All right, let's look at what this one here looks like. So I guess we're going to isolate, I guess, everything that's got the power. So we're going to add 9 to both sides. It's going to get us to 25. So all of this stuff raised to 2/3. And then we're going to raise, or we're going to, raise both sides here to the reciprocal fraction. So raise both sides to 3/2. Okay, and that should cancel everything out there. 25 raised to the 3/2 is the same thing as the square root of 25 cubed. The square root of 25 will be 5, and then 5 cubed, I believe, is 125. And then we still have x minus 4 over on the left side. Okay, and since we did a square root, we need to make sure we do plus or minus. So that would be plus or minus 125 right there. So then actually the answer comes out as two separate answers. You can say it's 4 plus 125 or 4 minus 125. So you got to be really careful there with that since it was a square root here. And I'll bring up a little trick here to remember that in just a second. This will come out to, I guess, 129. And then 4 minus that, that'll be x equals negative 120, or not even, negative 121 right there. And those are your two answers. So they split up into two separate answers in that case there. So here's a big question I always get. How do you know if you need to do it plus or minus? If you look here, if the denominator of your fraction after you raise it, so after you do the reciprocal of both sides, if the denominator is even, that means it's going to be like a square root, which means you need a plus or minus. So you need your plus or minus. If the denominator is even, then you need a plus or minus symbol with these here. For example, that denominator was 2. So that was like a square root, which means we need to do plus or minus. Even if it was a 4, even if I had something like this, let's make one up here. So if I had like the 4th root, x to the 4th, I don't know, is like 16 right there. I'm asking myself, what times what times what times what gets me 16? And I do the 4th root of both sides, which is, you can say it's like, I guess you can write it this way here. Sorry. And say, raise it to the fraction 1/4, raise this to the fraction 1/4. Notice the denominator is even right there. And like what we're saying, it is the 4th root right there. The 4th root of 16 right there is not just 2, but it's plus or minus 2. There's two different numbers. If you go back to the original question, If you go back to x to the fourth, we could have 2 times 2 times 2 times 2 and get us 16. Or we can do negative 2 times negative 2 times negative 2 times negative 2 and also get us 16 right there. So whenever your denominator is even, then that is when you do the plus or minus symbol. So whenever you raise both sides to the reciprocal and that denominator of the reciprocal is even, plus or minus both sides. Okay, let's try out another one here. All right, C. So first of all, get rid of that 3 out in front. And that'll be x plus 1 right there. That'll be, I guess, 4. And then you got raised to 2/3. All right, and then here we need to raise it to 3/2. Notice the denominator of the reciprocal is even. So that means we need a plus or minus symbol here. Plus or minus the square root of 4 cubed. Okay, if we do that there, what do we get? So that's the square root of 2, or square root of 4 is 2. So we'll go plus or minus 2 cubed, which gets us, I guess, plus or minus 8. And then we'll have to subtract over 1, so we'll do negative 1 plus or minus 8, which means negative 1 plus 8, which gets us 7. Or negative 1 minus 8, which gets us negative 9. And those are our 2 answers right there. Once again, that was because the denominator of the reciprocal was an even number. Let's try another one here. Add 9. That'll get us, I guess, 32. Okay, divide both sides by 2. That'll get us 16. Then raise both sides to the reciprocal to 3/4. Okay, denominator of the fraction is an even number, so we'll need to do plus or minus, and then that's the 4th root of 16 cubed. We can do the 4th root first. The 4th root of 16 is going to be 2. And then 2 cubed is going to be 8. So we got plus or minus 8 in this case again. We'll add 3, so it'll be 3 plus or minus 8. And that comes out to 2 answers. X equals 11, and then x equals negative 5. And those are your 2 answers there. All right, with this one here, they give us a meteor crater in Arizona. Uses this formula right here. It relates the diameter of the rim in meters and then the volume in cubic meters. What is the volume of the meteor crater? All values are approximate here. So what's nice about doing these types of real world equations is we don't have to worry about plus or minus type of stuff here, because you really can't have, negative, I guess in this case, diameter or a negative volume. So that's very nice. Also, second thing that they kind of throw us off with here is they give us how long the diameter of the crater in kilometers, but then notice our formula is built for meters. So we're going to have to take that 1.2 kilometers and convert that first of all. So 1.2, really, to convert from kilometers and meters, you just need to multiply by 1,000 right there. So that'd be 1,200. Okay, and then once we have that, now we're going to plug that in for D, and we should be good to go. So divide by 2, you got cube root, and V divided by 0.03, or 0.3, I guess I should say. All right, and then first of all, you want to get the radical by itself, so we'll divide both sides by 2. I'll get a 600. Then that'll be the cube root. You still got V divided by 0.3. Okay, to undo a cube, we're going to cube both sides, which is probably going to get us a real large number here. Let me grab my calculator. So cube both sides, 600 cubed is this giant number, 2,100. Hey, actually, let me count how many zeros. 1, 2, 3, 4, 5, 6. All right, so that is 216, I guess, million right there. And that's equal to volume divided by 0.3. And then to get rid of your 0.3, multiply both sides by 0.3. Okay, so times by 0.3. And that gives us an even smaller number here. This would be 64, I believe. 64 million. And then this is in, I guess, meters right here. So in meters cubed, actually. So there you go. That is how you do that problem right there. So just big things to look out for is watching out for your units. But pretty much all of the steps that we've been doing above and, in the previous days, getting rid of, cube roots and that type of stuff, you cube both sides and you'll be good to go. Okay, let's see what's going on here with this one here. You can model the population P of Corpus Christi, Texas between the years of 1970 and 2005 by this radical equation, or X is year. Using this model, what year was the population of Corpus Christi? 275,000 right there. Okay, and let's make sure they don't have anything weird going on with the units here. I don't think so, so yeah, we'll just take that right there. We're going to plug it in for P. So 275,000. Then you got the 75,000. And then cube root X minus 1950, because I guess that's when it started. So we're going to get rid of this 75,000 by dividing both sides by 75,000. Not sure if that's going to go in super well, but we'll find out here. So 275 divided 75,000, that comes out to about 3.6 repeating. And then I guess we got cube root of X minus 1950. All right, once again, to get rid of a cube root, we cube both sides. So I'm going to raise both sides to 3. It's going to get us 49.296 there after I round. And then I guess I need to add 1950 to both sides. And that comes out to 1999.2. So I'm just going to round it to 0.3 right there for the X right there. All right, so, sometimes with these word problems, you want to be kind of specific here. That's, how far, it was 1999 and then 0.3 of the year, or 0.3 into the year of when the population was at the 275,000 right there. So sometimes the question will word it to where it's like, what year was it over that amount? I guess they didn't really be specific here, so I'd just probably say about 1999 is when that population hit. But if it says something like over or under, then that's when you would consider that and round up or down, depending on the problem. But I think other than that, I believe that is it here for the lesson.